We left off last time, so we talked about the atom. We talked about, again, some of the experiments that led to the understanding of the atom, the structure of the atom. We also talked about, I believe, atomic number, mass number, and how to calculate the number of protons, electrons, and neutrons. Then I think we got into the atomic mass as well and how to calculate that. And I think that's where we left off, if I'm not mistaken. So we talked about to calculate the atomic mass. Basically, if you have multiple naturally occurring isotopes for a particular element, we basically take the percentage of the isotope times the atomic mass of the first isotope. Then we add it to the percentage of the next isotope times the atomic mass of that isotope. And however many you have, you sort of continue that pattern. And that is how we do get the numbers that we see on the periodic table, which are the numbers that we see below the actual element there on the periodic table. Those are, as we talked about, really average atomic masses of all the naturally occurring isotopes for a particular element. And remember that your percentages here should add up to 100%, right? Otherwise, you are missing some type of isotope. You could also use that to your advantage. You know, for example, if you're just given one isotope was 51% relative abundance, and you weren't really given the percentage of the other, you could simply just subtract from 100, and that would give you the percentage of the other isotope, assuming that it is just obviously two naturally occurring isotopes in that particular case. So I believe we ended with, we didn't do this one, we did the one before this, correct? Is that right? Yeah, okay. So why don't we do this one and see what we come up with? Bless you. So bromine has two stable isotopes, bromine 79 and bromine 81. The atomic masses are 78.92 and 80.92. Determine the average atomic mass there. So hopefully the right answer is up there. Take a minute or two and see what you come up with. Okay, so let's take a look. So remember that basically these percentages were sometimes referred to as their abundance or percent abundance, relative abundance. It's really the percentage at which that isotope occurs naturally in nature, obviously. One thing you do want to just make sure is just quickly look at those percentages. And again, it should add up to about 100%, which obviously it does, maybe a little bit more than 100%, maybe a little less than 100%, but it should be somewhere in that 100% range. Again, if you do that and you're like not at 100%, there should be some more information and there's another isotope sort of missing. So we basically have the percentages of each of those. They do add up to about 100%. So we really could just plug it into our formula where our atomic mass will equal our first isotope. Remember, you have two options on this. You can either just move the decimal place 2 places to the left or divide it by 100, which will move the decimal place for you. So on this first one, I'll just move the decimal place to make 50% there, 0.570. We would then times it by the atomic mass of that first isotope, which is 7892 AMU. Also, as we talked about last time, this is a place where people want to always multiply, but we're actually going to be adding here instead of multiplying. And we're going to do the same thing for our other percentage. Again, if you don't want to move the decimal, you can, like I said, divide it by 100. And that basically will move the decimal for you if you like to do it that way. And we'll times it by the atomic mass of the other isotope, which is 80.92 AMU. And if we do all that good stuff, so basically 0.5070 times 78.92 plus 0.4932 times 80.92 gets us a 79.92 AMU as the atomic mass there of bromine, which is pretty close to what we do see on the periodic table, about 79.9 grams per mole. Question on that calculation there. So again, variations of this, like we maybe talked about last time, is maybe they actually do give you the atomic mass, like what we just calculated there, and maybe they want you to find. Thank you very much. Maybe they want you to find the percentage of one of the isotopes or the atomic mass of one of the isotopes. So there's some variations on that. Any questions on that calculation? Okay. Oops, wrong way. All right, so next we're going to talk about is the periodic table. So that's the periodic table right there. So this is the periodic table. Obviously, the periodic table contains a lot of information on it. It obviously shows us all the sort of elements that we deal with. So let's talk about some of the important parts of it. When we look at a periodic table going sort of up and down, if you will, in a column, that is what is sometimes referred to as a group. And a family, if you're really old like me, not too many people call it families anymore. Most people call them groups. When we look at groups, there are several different numberings that perhaps you can see on this periodic table up here. There are some periodic tables have what is sometimes referred to as an A numbering, some have a B numbering, some have no letters and just run straight through to like 18. On pretty much every periodic table, we use what is referred to as the A numbering, and that is the representative numbering. And what that means is group 1 is actually here. So I'll just write a big 1. Group 1 is here. Group 2 is there. We actually skip the middle part here, and group 3 is here. Group 4, group 5, group 6, group 7, and at the end there is group 8. By the way, even though hydrogen is right here, it's actually not part of group 1. Group 1 starts with lithium, and we'll talk why that is in just a second. But that is the group numbering that we use, which is usually the A numbering. Most people don't say group 1A, they just say group 1, they say group 2, but it's sort of understood that they're talking about sort of the A numbering there. We very often don't use very much of the numbering in the middle. But some people will still use some of it in terms of B's numbering as you go through there. Now, going left to right, kind of like where I drew my arrow here, on the periodic table, those are called periods, and there are 7 periods on the periodic table. Period 1, period 2, period 3, period 4, period 5, period 6, and period 7 going left to right on the periodic table. We also already talked about the atomic number earlier in this chapter. Again, that is the number of protons, right, that you have. And that number is the number that we can find on the periodic table. So again, when we look at hydrogen, that is number 1 there, which would be its atomic number. And that obviously is the number of protons that it has. As I think we talked about when we were doing sort of atomic number and all those things, if you look at this periodic table, or really any periodic table, every single element has its own unique atomic number, which means every element pretty much has its own unique number of protons. And as we talked about, it is the protons that's really important in terms of determining what element you're talking about. So if you know the number of protons, you know what element you're talking about. If by some chance the number of protons changes, you're no longer talking about the same element, because that is really what determines what element is. We also just saw a second ago, just talked about a second ago, on the bottom there is the atomic mass. And right, that is our average atomic mass from those naturally occurring isotopes, the number that's on the bottom. So for example, hydrogen is 1.008. By the way, when we do go to the periodic table and use a number like what we see on the bottom, depending on your periodic table, you may have a lot of numbers or maybe rounded a little bit. But typically speaking, 4 significant figures, when you pull a number off of the periodic table on the bottom there, is typically how far you take it, or sort of for a usable sort of number. So just keep that in mind as you do calculations a little bit later on. We will be pulling that number off the periodic table to do some calculations. And just specifically speaking, 4 significant figures is typically what you kind of take. I don't think this book does it, but here at the old book, they used to have a weird rounding. They would round very oddly. But again, depending on your periodic table, you may see a lot more numbers than other tables. Now, The periodic table really is broken up into 3 different categories. And on most periodic tables, like I have here, that green sort of line that was there, there's usually something that is sometimes referred to as a staircase. And it usually is found starting up here by boron. And it kind of comes down like a staircase, hence why it's called that. Pretty much to the left of that staircase, we pretty much have metals. To the upper right of the staircase, we have non-metals. And what's on the staircase there, kind of in the blue boxes, if you will, these guys are what are referred to as metalloids, and they're sometimes also referred to as semi-metals, same thing. Now, metals are good conductors of heat and electricity. They can be pulled into wire. They usually have a very shiny appearance. For the most part, all metals are solid at room temperature except for one, which is mercury. Mercury is a liquid at room temperature, Hg. That's why on a lot of periodic tables, maybe not that one, but a lot of periodic tables, you'll sometimes see it as sort of a different colored font to indicate that it is a liquid at room temperature. Now, earlier I said group 1 really does start right here with lithium, and right above it is hydrogen. And that is because hydrogen is a metal or a non-metal. What is it? Hydrogen is actually a non-metal. Well, it's actually a non-metal, right? So it's the same color as what we have over there. So hydrogen is actually a non-metal, and lithium and everybody underneath there in group 1 are metals. And that's why group 1 really starts with lithium, because it is actually a metal and hydrogen is a non-metal. Hydrogen has a lot of unique sort of properties, and years ago, they don't do it too much anymore, but years ago on periodic tables when they were making for like rooms like this, you would sometimes even see hydrogen on both sides of the periodic table, really because he's a non-metal, he kind of goes over there, but for other reasons, he's on the left-hand side of the periodic table. So this is why when we talk about group 1, it doesn't really start with hydrogen, even though on pretty much every periodic table you see, he's over there. He's actually a non-metal when we look at it. Any questions on that there? Now, non-metals do have a little bit different sort of characteristics, obviously, than metals. They are pretty much the opposite. They're bad conductors of heat and electricity. They also have a more varied sort of state at which you can find them. They're usually dull and they're brittle. They're used for insulators a lot of times. So for example, things like nitrogen, oxygen, chlorine, as you guys said, hydrogen as well, those guys are gases under sort of normal conditions. Things like bromine, which is Br2, is kind of a liquid with like a little bit of vapor that usually comes along for the ride with it, a little bit of gas. And things like carbon and sulfur are solids. So a much wider variety of states we do see with our nonmetals, which again, for the most part, up and to the right of that staircase, also our hydrogen that's over here. Now, right there at that staircase, those are our semi-metals, our metalloids. And just to overlay it, some books include boron, some books don't. I don't remember off the top of my head sort of what your book does or not. But boron, for every other purpose, is sort of treated like a non-metal in terms of naming and stuff like that. But we do have this sort of staircase that comes down. And metalloids are pretty much guys which you might imagine have properties that are very similar to metal properties, and the same element has properties that are very similar to non-metal. So if you think about where they're located, they're kind of like the bridge between metals and non-metals, if you will. So they actually kind of can fall on both sides in terms of their characteristics. The same semi-metal can have properties that would be usually classified for metals, while it could also have properties that will classify it as non-metals. That's why sometimes a lot of semiconductors are sort of in that region of the periodic table. Now, there are certain groups on the periodic table that have special names, and you do need to know them, starting with group 1, which, as we've been talking about, does start with lithium, really. Group 1 is what are referred to as the alkali metals. So the alkali metals is coming down here. Right next door at group 2, beryllium, magnesium, calcium, and all those good guys, those are the alkaline earth metals. Going all the way over to group 7. So a reminder, group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. Here at group 7 are our halogens. These are a lot of the guys that come as diatomic molecules like F2, Cl2, Br2 coming down this way. We'll see it on the next slide. But group 8 also has a special name. Group 8 are our noble gases. Now, a couple of things, alkali metals, alkaline earth metals. In case you don't know, the word alkaline means basic, if you will. And a lot of really strong bases, things like sodium hydroxide, potassium hydroxide, calcium hydroxide. These guys all come from kind of group 1 and group 2. So it's where we kind of originate a lot of the strong bases, hence why their names are sort of alkali and alkaline earth metals. A lot of acids, by the way, are non-metals that come together with water on the other side. So you do need to know, again, group 1 is the alkali metals, group 2 is the alkaline earth metals, group 7 is the halogens, and group 8 is the noble gases. Any questions on that there? As I mentioned, our noble gases basically are, again, if you're really old like me, sometimes people used to call them rare gases. Most people, again, call them noble gases. Noble gases are what are referred to as being chemically inert, and that basically means they're very unreactive. So they're guys that are very unreactive. They'll react with themselves, but pretty much nobody else. So they'll play with themselves and nobody else. That's why they're referred to as noble, set apart. They are referred to as being chemically inert. There's also some noble metals, things like gold and platinum. Those are also very unreactive sort of metals that we come across. The 2 rows on the bottom are actually set aside so your periodic table doesn't take up the entire wall. And we can see if we follow the numbering, this is 56, that's 57, and then we jump to 72. The row that should be right there is actually 58. And same thing right below it, we go 88, 89, and like 104. The 90 here is what should go here. So these 2 rows at the bottom actually should go, technically speaking, right there on the periodic table. I've never really seen that happen except once, and it literally did take up an entire wall. They decided to do that for some reason in that room, and they made this periodic table where they had those 2 rows and everything else was to the right, and it took it up. But most of the time they're what are referred to as the lanthanides and actinides. Those are the 2 elements where they should follow on the periodic table. We really don't do too much with these guys. This is where a lot of radioactive sort of elements are. Things like uranium and a lot of sort of man-made guys, like Einsteinium and all those kind of guys that are really sort of radioactive. Transition metals are found between group number 2 and group number 3 on the periodic table. So right here between group 2 and group 3 on the periodic table, those again are our transition metals. Transition metals, as we'll talk about when we talk about naming, have special properties. One of the unique properties of transition metals are that they can make multiple types of charges. So, something like copper could be +1 in certain cases. Copper could be +2 in other cases. So transition metals are found between group number 2 and group number 3. This right here is what is sometimes referred to as the first row transition metals. And obviously the second row and so forth. That's why these 2 guys on the bottom are also sometimes referred to as inner transition metals. Because technically speaking, they should be in that spot where I drew earlier in the transition metal region. Any questions on any of those things there? So for the periodic table, again, you need to know where metals are found on the periodic table. You need to know where non-metals are found. You need to know where metalloids are found. You need to know some properties of each of those things. You also need to know, obviously, the proper numbering, group 1 through 8. You need to know which way periods go. And you need to know the names of the alkali metals and obviously where they are, alkaline earth metals, halogen, noble gases, and obviously where the transition metals are. Any questions on any of that? Okay. All right, then we're gonna kind of talk a little bit about the modern atomic theory. We're really gonna kind of focus in here on electrons and sort of electron configuration and where we sort of find a lot of things. First off, a lot of what happens with electrons are that they will sometimes get excited. And for example, if we have an electron at a lower energy level, we'll just use an arrow here. And it gets excited, it will find itself being promoted, if you will, up to a higher energy level. And much like us in life here, things like to be in a lower state of energy. So what will happen is eventually this electron will really want to kind of work itself back down to a lower state of energy. In order to do that, there's sort of the conservation of energy, which means, you know, the energy's got to go somewhere. And as those electrons are doing that, they will give off the energy, usually in the form of a wave, which is sometimes referred to as a photon of light. And if that photon of light, for example, falls within what is referred to as the visible part of the spectrum, we will see color. It's basically the principle behind fireworks. They shoot off fireworks, there's elements in there, they explode, which provides a lot of energy. All the elements, electrons get really excited, jump to a higher energy level, start dropping back down, and they give off specific colors in terms of photons of light. And we go, ooh, pretty red and pretty green fireworks, you know. So that's basically, you know, what's sort of happening when we do that. Now, not all sort of energy that's given off as, for example, electrons transition, are they always sort of in what we refer to as the visible part of the spectrum? And that's where we see colors in the visible part of the spectrum, like that Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. They may be in other parts, like infrared part of the spectrum, where we may feel heat, UV part, and so forth. So this is the electromagnetic spectrum, and there is a relationship to waves when they come off and energy. If we have a wave that has a short wavelength, it will have a very high energy and also has a high frequency. It occurs a lot. If we have a wave that's a little bit more sort of stretched out, if you will, has a longer wavelength, and it usually has a lower energy associated with it. So this is electromagnetic spectrum. So for example, on this side of the spectrum here, we have a much longer wavelength. On this side, it's a much shorter wavelength. And in terms of energy, it increases as we go to the right here on this scale. So over here on the left, we got things like radio waves, right? We listen to the radio in the car, not too bad, right? By the way, when you dial your radio into a specific station, you're actually dialing into a frequency so that you could hear the radio, right? When we go 95.5, that's really 95.5 megahertz, which is a frequency as you dial in your radio. Going a little bit to the right of that, we get microwaves to come off. Microwaves basically has a little bit more energy, enough to spin the water molecules really fast in your food. You get a pizza like in 3 minutes, which is a good deal. Moving to the right of that is infrared. That's usually where we feel heat and energy sort of coming off, a little bit more energy. We then kind of move into the visible part of the spectrum, which is up here. This is the visible part of the spectrum. It's actually all these colors right here. And again, that is where we do see colors. So again, if sort of the energy being given off, like in the firework example, corresponds to a wavelength that's within there, you know, we will see it. Even within colors, there's a different amount of energy associated with it. Red actually has a longer wavelength than, say, violet or purple. And violet has actually more energy than a red wavelength that's coming off. After sort of the visible part of the spectrum, we have the ultraviolet part, or UV. That's why we put sunblock on right when we go outside in the sun, so we don't get too burnt, because it's not so good to absorb a lot of that energy. It's very high energy. X-rays also shorter wavelength, much higher in energy. Why'd they throw a lead vest on you and leave the room when they shoot the X-ray, right? That's probably a good idea. They do those things. And then gamma rays is really just kind of a radioactive ray. That's really just pure energy. It's very, very high in energy. So, you know, as electrons transition, as atoms sort of give off energy as this occurs, you know, you may find yourself somewhere along this sort of spectrum. Any questions on that there? Here's maybe a better picture of that so we can kind of see all those things. But again, on this one, longer wavelength over here, lower energy. And on this side, shorter wavelength and higher energy. All right. All right, identify the form of electromagnetic radiation in each pair that has the greater energy. So again, even within colors, as we talked about, yellow light versus blue light, remember on this side is the longer wavelength. On this side is the shorter. So if we look at yellow, it is on this side and blue is over here. So the one that should have the greater energy is blue. Ultraviolet versus infrared. It is ultraviolet. It is past there, the wavelength that we have for visible spectrum. X-rays versus microwaves. I'm going to go with X-rays on that one there. Although they tell you don't stand in front of the microwave. I don't know. It's what your parents tell you, right? Like, don't stand in front of the microwave. Don't sit in front of the TV. All bad things. All right. So when we do have these sort of transitions of electrons as they move from different energy levels, they actually do give off a spectrum, and elements give off a specific type of spectrum, which is sometimes referred to as a line spectrum. And as you can see from the picture below, it's pretty much what describes what happens. So if you excite, for example, an element, and maybe you've done this experiment actually, like something like this, for example, you take like a gas discharge tube, put it in a lamp, they turn it on with some electricity going through it, excites all the electrons. You look at it with what they used to call a spectroscope. It has like a prism in it. It'll separate out the light. And what you will see is, because of those electrons transitioning from different wavelengths, every element will have a very distinct, what is referred to as a line spectrum, so distinct that you could basically determine what element you're looking at based on what colors you see come up in that line spectrum, based on what wavelengths they come out of. Every single sort of element has its own unique spectrum. That's really because every element has kind of their own unique number of electrons and their own unique ones that are going to be transitioning from different energy levels as well. So let's talk a little bit about energy levels. When we talk about energy levels, where electrons can be found in the atom, and that's sort of what we're going to be talking about here, is where electrons are going to be found in the atom. That is what is sometimes referred to as the principal quantum number, which is a very fancy word that basically just means energy level. And N can have values of, and that is abbreviated with an N. N can have values of 1 through 7. So there's basically 7 different sort of energy levels, if you will, within the atom. And on these energy levels, there's different amounts of electrons, depending on what element you're dealing with, as to where those electrons will increase. When we call N equals 1, that is what is referred to as the ground state. And that is the lowest in energy. So that is the lowest state of energy you could have, is the closest to the nucleus. As you go above that, N equals 2, N equals 3, and so forth, N equals 4. These are what are referred to as excited states. And those are higher in energy. So anything above N equals 1 is considered an excited state. It's considered a higher in energy. It's also further away from the nucleus as well. So you could kind of think of energy levels, again, building up. And where we find electrons, they could only really be on certain energy levels. So elements basically have what is sometimes referred to as quantized energy, which is a fancy way of saying you're going to find an electron on a specific energy level. When we talk about electrons sort of gaining energy, this electron is either on this energy level on the bottom, or it will gain enough energy to get to the guy to the top of them. And the same thing happens when it goes down. It will either be at this guy or it will lose enough energy to completely go down. The idea of this is kind of like when you walk stairs, right? You have enough energy to get to this step, right? You have enough energy to get to this step. You usually don't find yourself halfway between steps and say, I'm just going to relay it up right here. That's probably not going to go so well. And that's sort of how electrons transition from different energy levels. You'll either find an electron on this one, or it will gain enough to go 1, 2, 3 energy levels. Just like people when they walk stairs, some people have enough energy to do 1 step at a time, right? Some people can do like 2 steps at a time, right? Or 3. Probably not more than 3, I would imagine, or maybe. But same thing with the electrons. So they sort of gain and lose energy in what is referred to as sort of packets of energy that allows them to do sort of complete transitions from wherever energy level they start at to get to the next energy level. And that really does work both ways, going up in energy and coming back down in energy as they do that. And again, just to remind you in terms of what's happening, in order for an electron to go up in energy, it does need to absorb energy, right? So if we have an electron starting at a lower energy level, it actually has to pick up energy for it to come up. So kind of like what we were talking about with the fireworks, the explosion gives it all that energy. You throw on the lamp, it has electrical current going through it, gives those guys all that energy. It's absorbing all those energy. What we actually see a lot of times when we look at color is actually an emission type spectrum. It has to emit or give off that energy as those electrons are coming back down. You probably have done this yourself, perhaps, and maybe not even noticed that you did it. But if you've ever boiled water, maybe to make pasta or something like that, and it overboils, right? Because that happens. And the water hits the flame, what happens to the flame? It changes color, right, really quick. And that's really like sodium that's in your water. Basically, the electrons in it gets excited. It gives off really a distinct color of sodium, kind of like a flame test that you do while you're cooking dinner. And then you're upset because you got a mess you have to clean up. But that's sort of what happens there when you kind of see the flame change color really quick when the water hits it. It's really exciting those electrons, and probably from something like sodium that's probably in your water, even more so if you toss some more salt in there as you're making the sort of pasta. All right, so in each of the following energy level changes indicated if energy is absorbed, emitted, or not changed. So let's talk about these. An electron moves from the first energy level, which is n equals 1, to n equals 3. So we're starting over here. We're ending up here, our electron. Does it has to absorb or give off energy in this case? It does have to absorb. So this should absorb energy to allow it to get up there. Electron falls from the third to the second. So he's starting here, ends at the second. It would have to be emitted, right? It has to give off that energy and sort of emit it. Electron decides just to hang out on the third energy level and just kind of move around. There's going to be really no change, right? Because the electron hasn't transitioned to any other energy level. So there would be no change. Any questions on that there? All right, so as I talked about, our n values are really our different energy levels, and ultimately it's really where we can find different electrons within an atom and our excited states. Now, within these different energy levels, pretty much where electrons are housed are what are referred to as atomic orbitals. So atomic orbitals are really where electrons are housed in the atom. I believe we talked about the idea that, there's an earlier idea known by a guy named Bohr that, electrons move in these pretty little orbits and stuff like that, and they're just kind of circling around. and they really don't move that way. I believe we talked about it, but electrons move in a very random sort of pattern. And the idea was they sort of moved away from this sort of early idea that electrons move in these pretty circles in these orbits, like a planetary sort of model, to this idea of, you really don't know at any given point in time where a particle like an electron, how it's moving, or its location. And really
Bless you.